Like every good class, we're going to start by blowing something up. So this is a little box that I put together for my students. Before we build our computer kits, we play around with electricity and some electrical components to understand what we're actually building. So let me show you what's in our little box. I have a box of wire. Little wires, we'll see what they're used for in a sec. Some transistors. A bunch of different colored LEDs. And a bunch of different value resistors. A breadboard. We're going to learn how that works. A little power supply. And the components to hook a battery up to it and give us some electricity. And then finally, well, these fell out, a couple of little switches and a couple of chips. And we'll talk about what they do in a little bit. They're actually not part of the first lab, but they're part of a homework assignment if students want to do a little above and beyond outside of class. Okay, first thing we have to do is get the breadboard and power supply ready to go. And then we'll talk about exactly what we've done here. Okay, there are little jumpers on this thing. I need to move these over to the left side. This little power supply regulates the 9-volt battery down to 5 volts. Modern, well, at least modern in terms of the era that we're dealing with, electricity ran what's called TTL logic, and that's at 5 volts. We'll get into all that. That's all just kind of technical mumbo-jumbo that's not important for blowing something up. And then I need to make sure I align this correctly. Believe me, this will mess you up if you don't do it. That this little thing is going to plug into the breadboard. I'm going to describe what the breadboard does. But it matters that we align the negative and the positive with the negative and the positive here. Otherwise, our breadboard will be backwards, and that will blow stuff up in a whole new different kind of way. Okay, so what is a breadboard for? This is a way we can build stuff with electronics that makes it a lot easier. The idea here is that I'm going to plug in my 9-volt battery, turn it on, and there is now 5 volts going through this positive and negative line here, and positive and negative line here. And what happens is that the plus line going this way and the minus line going this way, which is actually ground, but minus depending on electrical stuff, and plus and minus, that is all now live. This stuff here in the center, if I plug stuff into one of these little holes, everything in that column that I plug in there will be attached to it. And just on like the north side or the south side are connected. They're not connected across this gutter in the middle. The gutter in the middle here is so we can plug something like a chip in there and then attach wires to the chip and build more complex circuits. So the first thing we have to do, turn that off. We're going to pop out one of our red LEDs and talk about what an LED is. None of the numbers on here matter for this lab. An LED is a light-emitting diode. And there's a little gap in here between the two pieces of metal. And what happens here is magically, through the magic of science, this will emit a little bit of light. And the polarity matters on this. Notice how one of these poles is longer? We have to make sure that's connected to the plus side, and the short side is connected to the minus. And there's another little hint. The minus side has a little divot in the plastic here. It's hard to see even in person. I can't imagine you're seeing that on the camera very clearly. So I'm going to plug this into the breadboard. And now I'm going to get a couple of wires out. And while not really important, the convention, not really important yet, the convention is that we attach black to the negative or ground side and red to the positive side. Okay, ready? It's going to be quick. See that little flash? We just destroyed an LED. Didn't quite blow up. Sometimes they even make a little noise. They're not dangerous. But what just happened here? We ran too much electricity through that LED. We basically shorted it out. And it's dead now. So I will throw it away because I can't tell you how frustrating it is to later use that in a kit and not know it's dead. So how do we prevent that from happening? Let's prevent it, and then we'll talk about why that worked. Gonna put in my new light. And I'm gonna grab one of these. And there is math that we can use to find out the right value. But I'm just gonna start with this 220. In fact, we'll try a couple and see what happens. There's that little symbol. We'll discuss that in a second. And now notice I'm moving the black wire over a bit. So this is not yet a complete circuit. I have the red wire going to the positive side of the LED, a gap here between the negative side and the black line, and I'm going to put in this resistor. Ta-da! And now we have a light that won't burn out. I'm going to now try one of these 10K resistors. So that's 220. This is 10,000. What will happen if I put a 10,000, that's called an ohm, a 10,000 ohm resistor in there instead of a 220 ohm resistor? Well, it lights up, but barely. My camera might auto-adjust that, but that is nowhere near as bright as the 220. In fact, if we were to put a bigger resistor in there, it eventually wouldn't light up at all. Before we talk about why, let's talk about how we would actually draw this circuit. So we draw this circuit like this. In fact, when we're drawing schematics, we don't typically include the battery in electronic designs like this. We just call a source that we are sourcing a plus 5 volt, and that we are tying the other side to ground. We are using an LED, which is drawn as a triangle with a line. The light's coming off of it. And then that goes to a resistor. And then that goes to ground. So what's actually happening here is electricity comes from the plus 5 through the LED to the resistor, which we typically label 220 ohm, and down to ground. And this shape is supposed to represent that electricity only flows one way, the direction of the arrow. This way it hits that wall. And the little lines represent that it throws off light. So why did that blow up with nothing? Why is it okay with the 220? And why is it dim with a 10K? Well, to understand that, we need to understand what electricity really is. And that's kind of a complicated thing, but there's a pretty easy analogy we can use to understand it. WTF is electricity anyway? We all know what that is. That's a 9-volt battery. 9 volt. What do we have 9 of there? We know what that is too. That's a AA battery. How many volts does a AA battery have? Does it have any? Why do we call that a AA and the other one a 9-volt battery? What is a volt? We can use water as an analogy to understand what a volt is. So this is Angel Falls. This is in Venezuela, and it is the tallest waterfall in the world. And you can imagine that waterfall falling over that cliff. By the time it hits the bottom, it's going really fast. It has a lot of pressure. It might even hurt if it hit you. If you remember your 7th or 8th grade science, you know that at the top of that cliff, that water has a lot of potential energy. And on its way down, it turns into kinetic energy, and at the bottom, there's no potential energy left. So, okay, the height of that waterfall is related to that amount of potential energy in that water. Well, here's a waterfall. You can imagine that waterfall. What is that? 15, 16 feet, maybe 30 meters? I can see a person standing underneath that, and they may be on par with where that rainbow is in terms of their height. So, I mean, that's a tall waterfall, but it's nowhere near as tall as the other one. So this one might be kind of fun to romp around under. There's just not as much potential energy in that water turning into kinetic energy by the time it hits the lake. Well, we can use this to kind of understand what volts are. A volt is a unit of measurement for the electric potential. We can think of it like the height that the electricity falls when it's flowing from the positive end of the battery to the negative end of the battery, or sometimes we call that negative end ground. You might also know the term amp. So what's an amp? Our homes have 15 amp circuits in them. What does that even mean? Well, this is Niagara Falls. We can think of an amp as the amount of water flowing over that fall. You can see that Niagara Falls is just huge compared to either of those other two waterfalls. It might not be as tall, but there is a lot more water going over that fall. An amp, short for ampere, is the unit of measurement for electric current. We can think of it like the width of the stream of water. So we can use volt and amp now to understand this a little bit. Here's a kid playing with a super soaker, and you can imagine that the harder he pulls back on that barrel, the more pressure that water is going to have as it's leaving that nozzle. So that's like adding voltage to that water. I don't know that he can do anything to adjust the amount of water coming out of it, so that's kind of like the amperage of this water gun. Let's compare that to a fire hose. That fire hose has a much higher voltage because that water is coming out under a lot more pressure. And it has a lot more amperage because there's a lot more water coming out of that nozzle. So that's how we can use volt and amp to understand what's going on with water. So why did that LED explode? Well, the LED exploded because we were putting this kind of water through it when it was expecting this kind of water. This one might make you a little wet, but this one's going to knock you on your feet. So we knocked the LED on its feet and blew it up. We need something that can control the water, the pace at which the water is flowing through the circuit. And that's what that resistor did. And we measured resistance in ohms. So what is an ohm? Well, an ohm is like the measure of the current of water that we can restrict with pressure. That's what the nozzle on this handle is doing. Notice that the faucet is not changing height. The voltage is set. That faucet can't come out and go lower. But we can make less water flow out. We can reduce the amperage of the water by turning the handle on that faucet. Then we can measure that pressure of that water, or that handle that's putting on the water, in ohms. And there's this little cartoon, kind of a famous cartoon that talks about this. You can think of amperage as the volume of stuff trying to go through this pipe, the voltage as the pressure on the stuff trying to get through this pipe, and the ohms as the restriction on the pipe that makes it hard to get through. So an ohm is the unit of measurement for the resistance electricity experiences when moving through a circuit. We can think of it like the dial on a faucet. And what we did with that resistor was dial down the amount of current that was going through the LED, and the LED didn't blow up. So there's another concept in here we need to talk about. It's not really part of the class when we're designing a computer, but I'm sure you know the term watt as well. This is Colvin Run Mill in Great Falls, Virginia. I grew up not far from here. An amazing tour if you ever get a chance to see it. And you can see that water wheel there and the water that's flowing over that little flume. And on particularly rainy days, there's a lot of water in there and that wheel is turning. On dry days, there might not be any water and the wheel might not turn at all. And you can think of all the machinery that's inside that mill. That's the cool part of the tour. They're grinding grain. There are things that are shaking husks off of wheat. There's a lot of machinery in there, conveyor belts and everything driven by that water wheel. So you can think that the amount of water, the size of that water wheel, the height of the water that's falling on the water wheel, all turns into some measure of work being done. And that's what a watt is. A watt is a measure of the power used when doing work. It's defined as the current of 1 amp flowing across the electrical potential difference of 1 volt. I haven't really talked about what these units actually mean. It's hard to put a real-world analogy on them. But the neat thing about watts, amps, ohms, volts is that they're all interrelated. Now, I tell my students when we're in this class that there's not going to be any math building this computer. That's because somebody else who designed the kit has already done all the math. But if we want to figure out the maximum brightness we can have that LED without blowing it up, we need to figure out the lowest ohm resistor we can put in that circuit. And that's what all this math is about. And it's really easy. Volts is just the amps times the ohms. And vice versa. You can just use algebra to pretty much figure out every other equation on this once you know one of them. Well, that's a useful rundown of understanding electricity. Let's use that to go play with our circuits a little bit more. I'm going to start by putting my 220 ohm resistor back in. Okay, and it should be nice and bright. There we go. Now I have here a little switch. We're going to add this to our circuit, and I'm going to make the switch control whether the light is on or not. May Ben Eater forgive me for using wires this way. His stuff is always so neat and pretty. He's a guy on YouTube. So let's see what happens here, and then I'm going to draw what this circuit is. My power's on, my light's not on. I press the button, and the light comes on. So I have my +5. I have a switch to my LED to my 220 ohm resistor and to ground. Right. 220 ohm. So that's my little circuit here. I can leave the electricity on, and yay, I have a light. I can now speak in Morse code to somebody. This sets us up for talking about transistors. So I have a transistor here, and a transistor is a little switch. Kind of like this switch, except where this is controlled by my finger, this switch is controlled by another electric current. Let me show you what I mean by that. Okay, you need to check this depending on your resistor that you're using. A transistor that you're using. But this transistor has a flat face and a bowed out face. And because the type of transistor that I'm using here, this is called a 2N2222. The 3 pins are the collector, the base, and the emitter. Let me wire that in and I'll talk about what that means. Okay, turning it on. My light does not light. Now this green line is now our control line. So I'm going to put this first in our negative side, just to show you that nothing should happen. Now it's wired up to negative, and the light does not come on. If I wire it up to positive, the light comes on. And now you might think, what's the big deal? You're putting electricity into a circuit and the light comes on. But the thing you have to understand about a transistor is that the electricity that is powering the light is coming from this red line through the white, through the LED, and out through the black ground. The electricity that is coming from this green line is not powering the light. And to prove that, let me take that really big 10K ohm resistor that I had. Oh, where'd it go? Well, these things are cheap. I'll pull another one. And let me connect the resistor through this line instead of the green wire. Now remember, with the 10K before, it was really dim. I hope that shows up on camera. But now it's really bright. So a little bit of electricity, remember the current here is really constrained through that resistor. A little bit of electricity is controlling a lot of electricity. And this is what makes a transistor a little miracle of nature. You can almost think about it like, imagine if you had a drip from a water faucet controlling the, a power generator at Niagara Falls that could turn the water on and off. A little amount of water is turning on and off all that huge water on Niagara Falls. That's exactly what's happening here. a little bit of electricity is turning on a lot of electricity. So we'll talk about what that means in terms of a digital signal in a minute. But think about what this means in terms of like a radio. You have a little electrical signal coming from an antenna, and it goes to control a much larger electrical current that's controlling a speaker. That's an amplifier. That's what transistor radios were all the big rage about in the 1970s, when all of a sudden radios didn't have to fill the size of a room. Well, the size of a cabinet. Here I have some old school tubes. Let's see these things. Now, old school tubes, come on. Old school tubes worked kind of like a transistor. They were much bigger. In fact, this is a small one. They were a lot more power hungry, and they got hot, and they took time to warm up. That thing doesn't get hot, well, at least under normal operations. It doesn't take any time to warm up. And by our standards, that thing is enormous, right? There are 8 of those in this chip, maybe 20 or 30 of them in that chip. And the processor in the computer that you're watching this on probably has 12 billion of those in it. So why is this relevant to computers? Well, that's basically a brain cell of a modern computer. And to show you why that's useful, I need 2 of them. And I'm going to build a quick circuit here. Let me show it to you. We're going to build a logic gate. Here's the circuit we're going to build. Okay, so here's our little diagram. We're going to have our plus 5 volt come in and go across this 1 kilo ohm resistor to this junction. At the junction, we're going to siphon off a little bit of that electricity to an output line that's going to be our LED and our resistor, and then to ground. Over here, we're going to attach one transistor and then another transistor. A couple of buttons with resistors on this side. All that's going to go to ground. And here's what happens. That light is going to be on until we do something. We push button A, nothing will happen. We push button B, nothing will happen. We push button A and B together, and the light will go out. And it's like, what? First of all, why does it do that? And second, why is that even useful? Well, the reason it does it is because we can think about normally the electricity is going to come over this resistor and go out to the light bulb and across a resistor and out. The minute I press this button and this button, both these transistors turn on, and the shortest path for that electricity is now from the plus 5 through that resistor, through the transistor to ground. The shortest path no longer involves that light because the resistor on this side. That light will not light up. And we have this little thing here that we call a truth table. And so when A and B are off, we represent that with zeros. The light will be on, we represent that with 1. So off is on, on is on off is on, but on is off. And this is called a NAND gate. This is our first logic gate. And the neat thing about a NAND gate is it is the universal logic gate. Anything that a computer can do, we can make it do with just hundreds, thousands, millions, or billions of NAND gates. In fact, we're going to use this in just a minute to build 1 bit of computer memory. That is, we're going to build a little thing that can remember if a button has been pressed or not. I don't have the control lines in yet, so this light should be on, and I really have no way to turn it off yet. Now let's add the buttons. Okay, let's turn it on and see what happens. Okay, my light is on. Press the first button, it stays on. Press the second button, it stays on. So now we debug. Well, that was fun. After getting out a pair of my old man eyes, and rebuilding a bit of the circuit, I fixed whatever was wrong with it. I must have been off a hole or two when I had the wires and the buttons and the resistors lined up. But it's working now, so watch this. Let's turn it on, and the light comes on. I press the first button, and light stays on. I push the second one, and it goes off. So if my example before didn't prove to you that I was feeding that light with current from the resistor, think about what's happening now. I'm turning those things on and the light is going off. And that's because of what I explained before, the way the electricity is taking the shortest path through the circuit. So why is this NAND gate useful? Well, once we have a logic gate, we can level up. We don't need to think about all the ins and outs and the resistors and the current going and all that stuff. We can draw a very simple little representation of all of this. We draw a NAND gate by saying we have our A and our B inputs. And we draw a thing that looks like a gumdrop. Okay, that looks more like a square, but a gumdrop with a little dot on it. That means invert. And then we have our out. So this means and then that means not in our little logic symbol language. So this is not A and B. So if A is 0 and B is 0, that'll be 1. If that's 1, 0, that'll be 1. If that's 0, 1, it'll be 1. If it's 1, 1, it'll be 0. So why is that useful? Well, we can build circuits out of this thing. Anything a computer can do, we can make it do it with these. And the simplest possible circuit we can make is what is called a D-latch. So let's forget this part of it for now. We're just going to look at this part. And this part we're going to hook up to our light-emitting diode to ground. And this we're going to hook up to our buttons. And then that we're going to hook up to a resistor and our +5s. And then let me explain what this circuit does. Let's say that light is off. We can press that button all day long and nothing will happen. But if we press that button, we've turned the latch on. And then I press that button, the light will come on. I can keep pressing that button on and off, and that light will come on and off. If I press the button and take this button off, now the light will stay on. That light remembers what that button was pressed as when this signal is taken away. So now we press that button again, that light will go off because that one's not pressed. Let go, and the light's off. Press it again, press that button, take this one off, and the light will stay on. This is 1 bit of computer memory. And think about that. If you have a computer in front of you with 8 gigabytes of RAM, well, that's a gigabyte. Okay, so let's say a byte is 8 of these. A kilobyte is 1024 of 8 of these. A megabyte is 1024 of 1024 of 8 of these. A gigabyte is 1024, 1024, 1024 of 8 of these. So if you have 8 gigs in your computer, it's 8 times 1024 times 1024 times 1024 times 8 of these things. And that's literally in your computer, and it's literally a chip the size of your thumbnail. well, maybe a little bigger, but a chip the size of your thumbnail. That's why we have billions of transistors in our computers. So, for a homework assignment, after we spent a couple hours in the library building this stuff out, I gave my students one of these. That is a little logic chip that looks like this. Recognize that? It's 4 NAND gates. We give it a +5 signal here, a ground here, and inside this chip are 4 NAND gates. So if a NAND gate is 2 transistors and a few resistors, then this thing has 8 transistors and maybe 4 resistors inside of it. Probably more than that because of the ins and outs. So there's a lot crammed into that little chip, at least by 1978 standards when that was first invented. So we can wire this to be one of these. We just need to give it +5 volt, ground, a couple buttons in, a light out, and then a couple wires running around the chip. And that's a homework assignment that I gave my students for the next time we're at the library. And the neat thing about this is they'll build that out on a breadboard, and later in our curriculum, we can literally attach that to our computer and have our computer write 1 bit of memory into that, and then come back later and tell us what we wrote. So it requires electricity for that, so it's not quite a thumb drive of 1 bit, but it works. And students digesting this understand what this logic starts to do. There's a lot going on here. You think about this, okay, so like that is a +5 volts going in here.
+5 volts going in here, so that's going to be nothing coming out here, so nothing going in that. So there'll be a 1 coming here.
And it's a lot to trace through. Even this little thing gets complicated to try to mentally reason about. That's why we use computers for designing computers these days. There's no way a human could reason about the billions of these that are inside of a modern computer. So that was our first in-person meeting at the library for building our computer kits. If you hung on this long, I'm impressed. Thanks for watching.